Let's look at applications into physics. One of those consists in finding what is the force on one of the walls of a tank. For example, suppose that we have a tank with the following shape. Suppose that we have that this tank is full with water and that we want to find what is the pressure over one of the walls of this tank. For this, what we can use is the equation for pressure, which is rho g times h. This is the basic equation for pressure, which means rho is the density of the liquid that we have. In this case, we can assume that that's water. Rho is the gravity, the force of gravity. And then h is the depth of our fluid. So we're going to use this main equation to find what is the force. And in order to find force, we can apply pressure times area. So we're going to combine these two equations in order to find what is the total force exert on this side of the tank. So what we're going to do is we're going to start by drawing this side over here. And for this problem, let's suppose the following thing. Let's suppose that this is going to be 4 meters and that this length is going to be 20 meters. So we have a big tank over there and we want to find what is the force produced by water on this side. So by looking at this information, we have that the length for the top part of the tank is going to be 4, which is going to give us that these 2 points are going to be 2 and -2 respectively. With that information, if we assume that this is a semicircle, we can find the equation for this. The equation for a circle is x squared plus y squared equals r squared. So that means that in our case, we have that the equation for that bottom part of the circle is going to be x squared plus y squared equals 2 squared equals 4. And again, we're just considering the bottom part, which means the part only when the y coordinate is negative. So with this, we can start finding what is the pressure exerted by the water in a tiny horizontal strip. Usually we're going to look at horizontal strips of water because along this strip, the force of gravity is going to be the same, or in other words, the depth of water is going to be the same. We don't look at vertical strips because over vertical strips, we don't have the same depth. We don't have the same force of gravity. We have different ones. So what we want to do is we want to break our problem into strips where all of our parameters are constant. In this case, this strip is going to have the same depth along the whole thing. So we have that depth is going to be by the same, basically the same number. We can call it h to start. So we have that the pressure over this tiny strip of area is going to be what we had before, rho gh. Okay. Now we're going to use the fact that this shape is a circle in order to find what is the total force. As we said before, the force is given by the pressure times the area. So this will be rho gh. And the area of this strip, notice that is going to be just a tiny rectangle. So in order to find the area of this strip, we need to know what is the width of this rectangle and what is the height or the thickness for that rectangle. Let me write it down as this thickness. So the width of this is going to be basically the width of the entire piece over here. And the challenge would be to relate these two variables, the w and the h. The thickness, on the other hand, this one is going to be a little bit more straightforward because what we're doing in here is we're cutting our shape into horizontal strips. So we've seen this trick before. We have that this is going to be a delta H. That is going to be a delta H. If we translate everything in terms of x and y, since we already have the equation for the circle, then we will have the following results. We have that h is related to y. H is related to y. Say, for example, it's very useful to write down a point of reference. If I choose that to be my point of reference, there is a relation, a clear relation between the y coordinate of that point and h. We have that it's not exactly y, because remember y is negative, but it's going to turn out being negative y. In other words, the depth of that horizontal layer of water is going to be minus y. So this is the first important thing that we can notice. The second important thing that we can notice is that the x-coordinate is going to be the distance between the y-axis and the point, which happens to be half of the total width of this strip of water. So we have that w is going to be 2 times x. With these two, we can actually write down the equation for the area. Now the area for that tiny strip of water is going to become w times the thickness, but this would become then 2x times delta h, what we had before, which is 2x times dy. Okay? So we have that the area of this tiny strip of water is given by this. And the important fact over here is that we have a dy, which means our final integral needs to be in terms of y. In other words, we need to get rid of this x. So we can do this by going back to the original equation that related x and y. In other words, if I want to solve for x, we can solve it from that original circle equation. So we have that x equals 4 minus y squared, square root of that. So we end up having that the area of that tiny strip is going to be 2 times the square root of 4 minus y squared dy. Now it's time to put these two equations together, namely the pressure equation and the area equation, so we can finally find what is the hydrostatic force. So we have that the force is then going to be given by F equals pressure, which is rho g negative y. Remember that we found that h was negative y, times the area of the strip of water, which is 2 times the square root 4 minus y squared dy. So the only thing that I need now in order to consider the whole thing, this we can say that is just a differential of force. That is the force only on this layer of water that we have in here. If we want to find what is the entire force over the whole wall, it should be the integral of this part, which should be the integral of rho g negative y times 2 the square root of 4 minus y squared dy. Now notice that we have a bunch of constants, so all I have to do is put all those constants together. This will become then just the 2 times rho g negative integral of y square root of 4 minus y squared dy. Then before I proceed to compute the antiderivative, I just need to find out what are the bounds for h. In other words, h will go from what value to what value. In this case, this picture will go in y between -2 and 0. So those are going to be my bounds for this integral. That will be the integral from -2 to 0, the integral from -2 to 0. And again, remember, rho and g are constants. Those are specific numbers. And in this very particular case, we have that rho, if we consider this to be water, is 1,000 kilograms per cubic meter. And g is the regular gravity constant, which is going to be 9.8 meters per second squared. So at the very end, we just multiply by these numbers and we will get the final answer. So finally, in order to compute this integral, we would need to use a u substitution to solve this part. So we can say that the force is then going to be -2 rho g. And then let's use the following U substitution. U equals 4 minus y squared, making du equals -2y dy. Now this turns out to be very convenient because this is an expression that we can find by just putting these three parts together. So this actually will become the integral of the square root of u du. And notice how the -2 disappeared whenever I put them together. Now the bounds are going to change as well. So the bounds are now going to be between y equals -2, which gives me u equals 0, and y equals 0, which gives me u equals to 4. So the only thing that I did was to plug the bounds for y into my u substitution, and that gives me the new bounds for my integral. Now this integral, you can calculate it because now I can find the antiderivative of this. I have rho g. Then this will become u to the 3/2 divided by 3/2 in between 0 and 4. This will give me then 2/3 rho g. And then everything at 4, 4 to the 3/2, and everything at 0, 0 to the 3/2. So simplifying this a little bit will give me 2 rho g over 3. And then 4 to the 3/2 is going to be the same thing as 4 to the 1/2 and then cube, which gives me 2 cube, in other words 8. So this becomes 16 rho g divided by 3. And again, we can just plug in back the constants that we had at the beginning. 1000, 9.8 divided by 3. And this will give me the answer that I was looking for. I can find the approximation of this using a calculator, and that will give me about 52,266.7. And this, since we're using the international system, this should be given in newtons because we're finding force. So the only thing that we did was to sketch the picture for this, to find the cross section, then to find out what are the pressure and force, and then finally to plug all the parameters together into our integral. Then using a u substitution gives me the answer.